Hi all, I welcome you all to the next lecture today. Today we are going to start introduction to power cycles, right? In previous lecture we have covered the concept of thermodynamic relations, right, where various relations have been discussed. Today our focus will be on power cycles. So mainly power cycles are divided into two categories, right, based on the working fluid. One is air standard power cycle, another is called steam power cycle. So steam power cycle you might have already gone through, basic mechanical engineering. Those are called external combustion engines, right? Steam power plants. So steam power plants means their combustion will happen outside of the engine. From there, hot gases will come in, and those hot gases will be utilized to develop the mechanical work by routing that high temperature gases over the turbine blades, and turbine rotates and you get the mechanical work out of it, and then process continues. So working fluid will continuously undergo phase change process, right, and repeatedly it will become vapor, then it will become liquid, then again heat it up and become vapor. So continuously it will be operating and producing the mechanical work. Second types of power cycles are based on the air. They utilize air as a working fluid, not working fluid, air as oxidizer for carry out the combustion, and that high temperature hot gas combustion product will uh, uh, displace the piston, right, and that piston will be connected to the crankshaft and crankshaft will rotate and you will get the mechanical work output, right, in the case of internal combustion engine. And second category is there, that is called gas power cycle, where you will be generating the gas by burning the fuel in presence of oxygen. That oxygen means air you are taking from outside, and then combustible product will be expelled through the turbine, and the turbine rotates, you will get the mechanical work output from there. And finally that gases may also expand through the nozzle to provide the thrust. So when the gases are expanding through the nozzle, they will come out with very high velocity, as a result of which you will get the thrust in opposite direction of the jet velocity. The cycle based on that concept is called gas turbine cycle. So in air standard cycle, basically you will be discussing about the cycle which we are basically engine which we are using in the normal bikes, right, or automotive cars, and also we will be discussing the engines which we are basically using in the aircraft. So these both types of three or four types of engines and their working principle and the cycle on which they basically work will be discussed in this today's discussion. So already you have been given a general definition of a heat engine. Heat engine is a device which operates in a cyclic way, and the sole purpose of the heat engine is to provide the mechanical work for a given input. So what input you are providing to the heat engine is nothing but the given quantity of heat. So how much portion of the given quantity of heat is getting converted into the mechanical work, that is called as effectiveness or efficiency of the heat engine. So as per the second law, we came to know that the complete conversion of heat into work is impossible, right? So some portion of it has to be rejected to the atmosphere in order to produce the mechanical work in a cycle. So up to we know from theoretical calculation that Carnot cycle is the efficient possible cycle, or you can say it is an ideal cycle whose efficiency is 100%. That means only Carnot cycle can convert the given input entirely into the work, given input heat into entirely work, but that is not possible in reality. So an actual engine will have efficiency lesser than the Carnot cycles, but Carnot cycle need to be considered as a benchmark, right, for this sake of comparison. When you are designing any new device, you have to compare the performance of new device with the Carnot cycle. So let's start our discussion for today. So today we will be focusing mainly on air standard cycle, or the cycle which use the outside air for its combustion. So objective to study about the performance of a gas power cycle, for which the working fluid remains a gas throughout the entire process. Alright. To study the working of cycles, mainly our focus will be on Carnot, Otto, diesel, dual and Brayton cycle. So these are the basic cycles, right, which need to be discussed. And based on that, what are the different vehicles, right, that we are using in day-to-day life. So, what are the gas power cycle? So, gas is a working fluid basically here. So, here gas is the working fluid which does not undergo any phase change, right? Engine operating on a gas power cycle may be either cyclic or non-cyclic. So, hot air engine, particularly we talk about, they uses the hot air as the working fluid and operate on a closed cycle. IC engine, where the combustion of fuel takes place inside the engine cylinder, are basically non-cyclic heat engine. So if you talk about IC engine, it will have different kind of strokes and all processes are different. So they are known as non-cyclic. Come to the Carnot cycle. The fundamental thermodynamic cycle proposed by the French engineer Sadi Carnot in 1824. It was an attempt to explain the working of a steam engine. So Carnot cycle is one of the best non-reversible cycle, and the Carnot cycle is composed of four reversible processes. So you can say it is a cycle which is having effectiveness 100%, or you can say that all the processes associated in cycle are reversible. So if we look at the Carnot cycle, already some idea has been given to you in second law of thermodynamics. Carnot cycle is having four processes: two reversible isothermal and two reversible adiabatic. Heat addition and heat rejection takes place at constant temperature, and the work of compression, work of expansion, these basically are isentropic process or reversible adiabatic processes. So it start with basically heat input, and heat input takes place at constant temperature followed by the isentropic expansion, right, where you are getting the mechanical work 2 to 3, and then 3 to 4 is basically isothermal heat rejection followed by the isentropic compression which completes the cycle. So this is PV diagram, right, on pressure volume diagram. This is if you look at the isothermal curves, there will be inclined right curve, and this is the isentropic curve, that is expansion followed by the isothermal heat rejection then compression. So if you draw this over temperature versus entropy, we know that for isentropic process entropy are constant. So these two processes, isentropic process, can be drawn by vertical lines, and isothermal will be having horizontal lines. So these are horizontal lines. So this is heat addition followed by the isentropic expansion, then heat rejection, then compression. This is the basic cycle. And also we know that the effectiveness of Carnot cycle depends entirely on the temperature, right, maximum and minimum temperature of cycle, and it does not depend on the properties of the working fluid. So it is not going to make any sense either you are using air or you are using liquid inside the this cycle as a working fluid. Its performance will entirely depend on the maximum minimum cycle temperature. So two reversible isothermal and two reversible adiabatics, right. So if we consider if an ideal gas, right, as a working fluid, for 1 kilogram of gas you can find out the heat input, right, that is given by RT1 ln of V2 by V1. From where we are getting this? If you apply the first law of thermodynamics, as per that you can write Q1 to 2 is equal to U2 minus U1 plus W, right, W, that is called displacement work. So U2 minus U1 will be 0 because there is no change in temperature. So work in isothermal process is nothing but RT1 or P1 B1 ln of V2 by V1. V2 is volume at 2 and volume at 1. So heat input is given by RT1 ln of V2 by V1 for the process 1 to 2. Similarly, work input means work 1 to 2 will be exactly equal to what you are writing here, because heat transfer is equal to the work transfer. And process 2 to 3 is isentropic, means reversible adiabatic. There is no heat transfer involved in this 2 to 3, but there will be mechanical work out which is equal to change in internal energy, that is CV T3 minus T2. Similarly, similar expression you can write for this and write for this. So Q334 is RT2 ln of B4 by B3, and W334 is exactly equal to Q334, and Q421 again is isentropic process. Heat transfer is 0, but work is equal to minus CV T1 minus T2. So if we add algebraic summation of heat transfer and we put it is equal to algebraic sum of work transfer, both will be exactly equal. And also these are the isentropic relations that can be applied. So process 2 to 3 is isentropic, process 1 to 4 is isentropic. So we can apply these isentropic relationship of specific volume with temperature. right? And from these two, basically T2 and T1, this quantity is same, so we can relate V2 V3 and V1 V4 by this relation, or you can say V2 by V1 is equal to V3 by V4. All right. So if you substitute this, you can write heat added is equal to RT1 ln of V2 by V1, right? And heat T2 is RT2 V2 by V1, because V2 by V1 is equal to V3 by V4. That is not going to make any sense. So you can say net work output is Q1 minus Q2 is R ln of V2 by V1 T1 minus T2. So efficiency of cycle is nothing but W net divided by Q1. If you divide by Q1 this equation, you can get T1 minus T2 by T1. So from this equation, we can say that if T2 is low, right, T2 is going to be 0, or you can say the temperature at which heat is getting rejected is 0, we can have 100% efficiency. Right. Another important, output of this cycle efficiency is that efficiency of cycle is a function of temperature alone. So highest the temperature generation, or you can say the highest temperature that you are obtaining, right, in the combustion will have a direct impact over the cycle efficiency. But large drawback of this cycle is that this back work was particularly compression work is a bigger in Carnot cycle. If you are going to make it as a practical cycle, and compression work requirement is more, so overall efficiency will be less if you are going for practical application of the Carnot cycle. But theoretically, it is having maximum possible efficiency. So this is a benchmark efficiency cycle which need to be compare means we need to compare the any new device with the performance of the Carnot cycle. Next one cycle that came into existence in 1827 was the Stalling cycle. So if you look at the Stalling cycle, it is also having four processes, right? Two constant processes, heat addition and heat rejection is constant temperature process, right? And two constant pressure process. Sorry, not two constant volume process, right? Process 1 to 4 and 2 to 3, these are the constant volume. So if we draw this over the temperature versus entropy diagram, right, these are the constant volume process, these are the constant temperature process. So process 1 to 2 is the heat addition at constant temperature, followed by the process 2 to 3 is basically constant volume expansion, heat rejection and compression. Area under the curve, right, between 1 and 4 and 2 and 3 is representing basically work, so work of expansion, work of compression. So two reversible isothermal, two reversible isocores or a constant volume process. So we can write Q1 to 2. We are writing for this. Same expression you will be getting RT1 ln of V2 by V1, and Q2 to 3 is basically about expansion minus CB T2 minus T1, and W2 to 3 is 0 because this is a constant volume process, right? Constant volume process. And Q3 to 4 again RT2 ln of B3 by V4, and Q4 to 1 here you will get CVT1 minus T2, but work transfer is 0, right? Work transfer is 0 in the process 4 to 1. So keep in mind here heat rejection is taking place basically at constant heat transfers are constant volume press processes. In this process heat transfer is also taking place, right? Process 4 to 1 and 2 to 3, some heat transfer is taking place. That's why the efficiency of Stirling cycle is less than the Carnot cycle. However, if you add the regeneration arrangement to this, then this can be make up, and then you can approach to the efficiency of the Carnot cycle. So if you substitute these values of Q1, Q2 and Q1 in this, you can write the equation which is equal to T1 minus T2 divided by T1. Right. So this is with the help of regeneration. If you are adding the regeneration in the process 2 to 3 and 4 to 1, in that case you will get the efficiency equal to the Carnot cycle efficiency. Next one, erection cycle. Immediately after that, erection cycle came into the existence. So erection cycle processes are there are two constant pressure processes, right? These are the constant pressure processes and two reversible isotherms, right? Process 1 to 2 is isothermal, followed by the 2 to 3, then 3 to 4 and 4 to 1. So that can be drawn over the TS diagram. These are the constant pressure lines and these are the constant temperature lines. So here two isothermal, two constant pressure, and compared to earlier one, there were two constant volume processes. So in the erection cycle, expansion and compression processes are replaced by the constant pressure process. So process 1 to 2 heat addition followed by the expansion, then heat rejection and compression. So we can write the equation for Q1 to 2 is W1 to 2 R T1 ln of P1 by P2, and Q2 to 3 this is 2 to 3 constant pressure Cp T2 minus T1, and here work also you are getting. So if you compare with the Stirling, compared to Stirling, efficiency of erections will be more, right, without regeneration. Without regeneration itself, you can get the better efficiency. Similarly, same expression you can write for 3 to 4, right? That is equal to W 3 to 4, that is given by RT2 ln of P1 by P2. And Q4 to 1, again process is a constant pressure process, Cp T1 minus T4. And for constant pressure process, the work can be written as P1 B1 minus B4, right? That is also equal to, you can write P1 B1 is equal to RT1 and P2 V2 is equal to RT2. So RT1 minus T2. Since the part of heat is transferred at constant pressure and part of at constant temperature, the efficiency of erection cycle is less than that of Carnot cycle. Right? Compared to Carnot cycle, efficiency is less. But if you add, right, regeneration in the process 2 to 3 and 4 to 1, all right, then the cycle efficiency can easily approach to the Carnot cycle. So you can put the value 1 minus Q2 by Q1 is equal to 1 minus this term RT2 divided by RT1 P1 and P2. These both are the same, right? You can cancel out P1 P2. You can get 1 minus T2 by T1. Clear. So look at heat rejection is RT2 ln of P1 by P2. This is your Q2, and Q1 is given here RT1 ln of P1 by P2. These two things you have to take into account when you are adding the regeneration. This heat rejection, right, Q4 to 1 and one process here CPT2 minus T1. These are the cancel out. These need to be cancel out, right, if you want to approach the Carnot cycle efficiency, right? That in that case only this term and that heat, only two heat rejection, a heat transfer will be there, heat addition in process 1 to 2 and heat rejection in process 3 to 4. But additional heat transfers also you are getting, right? This need to be minimized. For that purpose, regeneration need to be added. Next one is reciprocating engines. After that, reciprocating engine came to the picture. So whenever we talking about the reciprocating engine, they will be visualized like piston cylinder arrangement. Piston cylinder arrangement. So look at the geometry. If we look at the geometry of it, it will have a cylinder, right? It is having a cylinder, and in within the cylinder, piston will be moving. Piston will be moving. So this is the cylinder basically. Inside that piston is there. This is the piston, right, which will be moving between two fixed point. One is the lowest point, one is the topmost point. The topmost point is known as top dead center. Bottommost point is known as bottom dead center. Right, over the piston head, this is called cylinder head. There are two valves. One is intake valve, and another is called exhaust valve. So intake valve will open to get the fresh air inside, right, and exhaust valve will open to remove the combustible product out of it, right, once you have got the mechanical work output of it. So the distance between top dead center and bottom dead center is known as stroke, right. The one motion of from bottom dead center to the top dead center is known as single stroke. All right. So if you look at this, right, when you are taking the air inside, right, your exhaust valve will be closed, intake valve will open, air will come inside. So and the piston will move down towards the bottom dead center. When it's going compression stroke, both the valves will close, right, and piston will move up. It will compress and will reach near the TDC. Once it reaches the near TDC, it has been compressed. Now your combustion has to be started. So you can initiate the combustion with the help of spark plug over here. So this volume, whatever is left with, right, when piston is exactly at top dead center, this volume is known as combustion volume, or you can say the clearance volume. Usually in bike we define like 100 cc and 150 cc. That cc is nothing but cubic centimeter. That is representation of volume. That volume is nothing but this volume. Larger this volume, larger heating can you can produce. So if you are going for larger cc, it will have larger power output. That is not clearance volume, right? Clearance volume. And displacement volume is that volume between top dead center and bottom dead center. Whatever volume has been taken off, right, by the cylinder from outside, that is known as displacement volume. Compression ratio is the ratio of maximum volume divided by minimum volume. So maximum volume where you will get at the bottom dead center, you will get the maximum volume. Minimum volume you will get at the top dead center. So volume at bottom dead center divided by the volume at top dead center, this ratio is known as compression ratio. Higher the compression ratio, higher will be the efficiency. Higher will be the efficiency. And the piston, if you look at the cross section of piston, will be a circular one, right? So the diameter of that piston will be known as bore, will be known as bore, and stroke is distance or point between which your piston travels, right, is known as stroke. Next one is mean effective pressure. If you draw the pressure versus volume diagram for this cycle, right, for this process, one piston is moving from top dead center to bottom dead center, it will be following this kind of curve. So it is basically moving between minimum volume and maximum volume. And over the piston face, the pressure which is acting is known as mean effective pressure, and that will be responsible for producing the mechanical work. So all around the surface pressure will be same. So mean effective pressure into volume change will give the mechanical work output. So W is equal to 1 to 2 PdV. So this P is mean effective pressure, dV is change in volume between minimum and maximum volume. Right, larger this quantity is, larger is the work output. So internal combustion engine, actually the idea about this was given by the Nicholas August Otto, and he invented the first cycle that is called Otto cycle. And based on Otto cycle, basically your automotive bikes and lightweight vehicles are working with. So conceptualized by the Nicholas August Otto on June 14 in 1876. Actually, he invented the auto cycle in 1876. He was born on June 1832 and died in 1891. So internal combustion is having four strokes, right, and two strokes. Two kind of configurations are there, but four stroke is more fuel efficient, and because there is a proper timing for combustion, and you can say near complete combustion is possible in the four stroke cycle compared to the two stroke cycle, and because of that is more fuel efficient and clean burning will take place. So Otto cycle consists of basically these four strokes: intake stroke, compression stroke, power stroke, and exhaust stroke. Intake stroke is the stroke in which inlet valve will open and piston will move down towards the bottom dead center. It will suck the air inside. Fresh air comes in, right? Then compression stroke start. Inlet valve will close. Then piston will move up, right, and compress the air. And the point your piston is reaching at the top dead center, right, your air will get completely compressed. Then your ignition will start. You will initiate the combustion with the help of spark plug. So all the compressed air fuel mixture, right, will get converted into the combustible gases, and that gas will have high pressure. Because of the pressure exerted over the face of the piston will move down. The moment your piston is moving down, right, piston is connected to the crankshaft with the help of connecting rod, and the crankshaft will rotate and you will get the mechanical work. Once you have got the mechanical work, then exhaust valve will open, right? Once the exhaust valve will open, combustible gases will start flowing out of the exhaust valve, and pressure decreases inside the cylinder. Because of that, piston moves from bottom dead center towards the top dead center. Then again cycle repeats. Then exhaust valve closes, open, and inlet valve opens, and cycle repeats. So this is the basic working of four stroke engine, right? So this is a very simple thing, right? Inlet valve opens, then this will move down, and so in this case this is the intake process. So inlet valve is opened, piston is moving down, right, and it will suck the air inside. Once this is over, right, then your compression will take place. Inlet and exhaust valve are closed, now piston moving up, so your compression takes place. The moment your piston is at top dead center, you will initiate the ignition with the help of spark plug. So high pressure and temperature gases will generate, that will push the piston down, right? So then piston will move down. So it is moving down, that is called power or expansion stroke, right? And after that, once your piston has reached at the top of the center, your exhaust valve will open, right? Once it will open, your combustible gases will come out and piston will move up, and cycle repeats. So this is the ideal scenario when all processes are reversible. You can represent the cycle as heat addition, right, at a constant volume, followed by the isentropic expansion, then constant volume heat rejection, then isentropic compression. This is the ideal case. This is the real case, real diagram. In reality, none of the processes are reversible, so they will be following in this way. So in summary, the Otto cycle basically having two isentropic processes, right? Uh, when work is produced or input, and two processes at constant volume where heat is added or removed. So heat addition and heat rejection takes place at constant volume, and work of compression and work of expansion, they do take place at isentropic processes. So to analyze actual cycle, right? To analyzing actual cycle is bit difficult, right? Because you look at this diagram, very difficult to normalize these processes and idealize this process. So it is very complex to study the actual gas power cycle. So simplest way is to simplify them to near ideal process and then find out the performance parameters. Those performance parameters will be the actual performance parameters of the cycle. So that's why here standard cycle came into the picture. So there are standard assumptions that need to be followed when you are doing the idealization of the process. Working fluid is air and is assumed to be ideal gas. Second assumption is that air circulates in the closed loop acting as an ideal gas whose specific heat is constant. So all processes are internally reversible. Next assumption is combustion is replaced by the heat addition process for an external source. And last one is exhaust is replaced by the heat rejection process that return the working fluid to the initial state. That means in actual case what is happening, we are taking the air inside and we are mixing the fuel inside in it at certain proportion, then we are burning it. The moment we are burning it, air will not be air, it will become the gas, right, carbon dioxide. So if we are not releasing that gas and we are again cooling it, when you are cooling it, it will form the carbon deposit, right? And you will not have a same mass of air inside, right? So over the period of time in second cycle, it will be very difficult to carry out the combustion because it is a basically gas, combustible gas having carbon percentage more, right? So less oxygen present, so burning will not be that much smooth and you will not be able to get the required combustion temperature, so performance will deteriorate. If you are going for third time, then there will be zero oxygen present, so combustion will fail. When combustion is going to fail, your engine will fail because of the carbon deposits on different reciprocating parts, so it will be a complete damage to the engine. Right, if we are simply thinking in that way, we are not exhausting the gases out. So if you want to get the actual performance parameters, then you have to assume like air is not undergoing any kind of conversion to CO2 or some other case. So we are considering like air is coming and we are heating the air to the required temperature in the combustion chamber with some external heat exchanger. Then finally the hot air is coming inside the piston, right, and pushing the piston down, and we are getting the mechanical work out of that. Then you are cooling it with some external cooler, so air again getting cool, again it will be recirculating inside the compression and then combustion, like that process will carry out. So air will not undergo any kind of heat change, right? But there what was happening, air was getting added with the fuel, and when we are burning it, it's getting converted into the carbon dioxide, right, CO2, and then further even after cooling you cannot make it separate oxygen, right? So that was the drawback if we are just analyzing the actual cycle. So instead of doing so, we are making this is an idealized cycle where air is as per working fluid, air is continuously circulating in this circuit and producing the mechanical work, and we are not adding any fuel in this. So this is basically the air standard cycle assumption, right? For today discussion, this much is enough, right? So if you are having any doubt in this content, right, you can feel free to write in the comment section, all right, or you can directly approach to me on my WhatsApp number. So today, as a summary, I will conclude. We have gone through the classification of power cycles, right? As I clearly said, Based on the burning fluid, we can classify the power cycle in two form. One is internal combustion engine, another is called external combustion engine. External combustion engine basically utilizing the steam, and steam is generated from the water. So that will fill in means outside of the engine. You will heat the water, you will get the steam, then you can utilize the steam to make to produce the mechanical work. Second classification is which is utilizing the air from outside. You are taking the air inside and you are mixing the fuel with the air, and you are starting the ignition inside a closed container, right? And at the end you are utilizing that hot high temperature pressure gases, right, to push the piston down, and piston is connected to the crankshaft. You are getting the mechanical work output from it. That is called internal combustion engines. So all the automotive vehicles, right, even all the possible vehicles which are we are using for transportation purpose are the internal combustion engines. And then finally, I gave you an idea, right, how actually we analyze these actual engines by replacing all the processes of engines by an equivalent ideal processes, right? And also you have given an idea about Otto cycle. Otto cycle is having total four processes: two reversible isentropic process, two reversible adiabatic process, and two reversible constant volume process. So heat addition, heat rejection take place at constant volume, and work of compression and work of expansion takes place at reversible adiabatic process. All right. And also you have seen clearly the various terminologies used in IC engine, right? Piston cylinder. You have been given a clear idea about stroke, bore, compression ratio. These are some of the important terminologies that need to be used when you are designing the internal combustion engine. So with this, I am closing the today's discussion. If you are having any doubt, feel free to approach me. See you all in the next class. Have a nice day. Good day.